honors level topic, we are going to talk about what happens and the trends for removing second and third electrons. So we'll look at some pictures for that. It'll work better if I do it this way. Okay, so let's look at sodium. And it has a number 11, so we're going to map 11 electrons. And we've got those 11 protons there in the nucleus. It's going to have 3 energy levels because it is on the 3rd row of the periodic table. So let's map these electrons. There we go. Okay, so I have my 11 electrons here. The first ionization energy for sodium is pretty low, and that was the trend we just talked about. It has 1 valence electron. It is not going to have any hope of collecting 7 more to be stable. So we're going to represent this as I1. That is the energy to remove first electron, okay, or the ionization energy for removing that first electron. All right, and so that's relatively pretty low. Now, if I remove this electron, that means that whole energy level is gone. Sodium now acquires a positive charge. Is sodium going to be happy with this? How many electrons does it now have in its outermost energy level? Because this one's now gone. 8. Oh, sodium's going to be all kinds of stable if it just loses that 1 valence electron. Does everybody see that? Has that 8 now. So I2, if I go to remove that second electron, and that's what that 2 means, or that 2 means. So if I'm trying to remove this electron, is sodium going to be happy with that? No, not at all, because then it's losing that level of stability. So the ionization energy for removing that second electron is going to be way high. You're going to see a big jump in the ionization energies. And a good reason for this, and you do want to make sure that you know the reason, is that it always takes more energy to remove a core electron than a valence electron. So it always takes more energy to remove a core electron than a valence electron. Partly because they're closer to the nucleus, proximity counts. Okay, so I've removed this electron and sodium is now at a 2 positive charge. If I try and remove a third electron, so this is my third ionization energy. So let's say I'm going for this electron. Is it going to require more or less energy than I2? Always more. Always. Because remember, the number of positive protons doesn't change. It stays there. And so now we've got still 11 protons, but now we're attracted to 9 electrons. So this one is going to be more. You're not going to see a big jump, though. It's just going to be a little bit higher than I2. It always requires more energy. But in this case, it's not going to be a big jump because it's already lost its level of stability. Yes?
When elements want to only have half the electrons, was that what we talked about with copper carbide?
Yeah, and that has to with electrons would rather be half filled than not half filled or not completely full. Yeah, that did have to do with the orbital designations here. Here we're talking about the whole energy level. Yeah. All right. So that's sodium. Now let's look at magnesium. It's going to be relatively similar here, but magnesium has 12 electrons. So we'll go ahead and draw that. 12 protons in the nucleus. We have those 3 energy levels. Okay. Now, how is the first ionization energy of magnesium going to compare to that of sodium? And this is our trends that we just talked about, our first ionization energy trends. As you go across, what happens to ionization energy? It increases. Okay, so the I1 for magnesium is going to be a little higher than the I1 for sodium, but not a whole lot more. All right, so still, because he doesn't have any hope of collecting 6 more electrons, so still relatively low. So now I'm going to remove the next electron. So I2, your second ionization energy. So I've removed this one. That was pretty easy. I2. Now I'm going to remove this next one. Is magnesium stable at this point before I've removed it? No. So is it going to require more or less energy to remove that second electron? Always more, always more. All right, but you're not going to see a big jump like we saw in sodium. So a little bit higher than I1. Okay, so now magnesium has this 2 positive charge. This energy level is gone because it's lost all of those valence electrons. Now, is magnesium going to be happy with this situation? Yes, it has a stable configuration and now has 8 electrons in its outer energy level. If I try and remove a third electron, that ionization energy is going to be, what do you think? Way high. Yeah, it's going to take a lot of energy to remove that core electron and leave that stable configuration. So way high. Okay, and that's removing that third electron. All right, so we can look at sodium, and that's going to be our representative for that first energy level, or the group 1, things with 1 valence electron. They all act like sodium. Magnesium is our representative for group 2, the alkaline earth metals. They're all going to act like this with their ionization energies. So what we're going to do is kind of make up a chart and see if we can predict some of the others. With sodium, it lost its 1 valence electron pretty easily, but the second electron, which was a core electron, the ionization energy, there was a huge jump in that. With magnesium, it had 2 valence electrons, and it lost those 2 relatively easily, but removing that core electron with the third electron is much more difficult. Okay, let's see if I can erase this. All right, so let's make a table, and let's talk about number of valence electrons and big jump in ionization energy. So we already saw that group 1 had a big jump in ionization energy. It lost its first electron pretty easily, so it was between I1 and I2. I2 had a huge ionization energy because that was removing a core electron. Group 2 has 2 valence electrons, and we saw that it has a big jump in ionization energy between I2 and I3. Removing that third electron, we've lost all of the valence electrons, and removing that third electron was way more difficult because it was a core electron. If we're talking about something from the boron family, so group 13, which has 3 valence electrons, where do you think you're going to see a big jump in ionization energy there? Between I3 and I4. So they're going to lose their 3 valence electrons pretty easily. And so I3 will still be relatively small. But I4, they've lost all of their valence electrons, and now we're trying to remove a core electron. And that's going to take way more energy. Does that make sense? Okay, and group 4, or things with group 14, which has 4 valence electrons, is going to have a big jump in ionization energy between I4 and I5. All right, does that make sense? Okay, this is, like I said, an honors level topic, and you are going to have to explain this to me on the test, so make sure that you can. I'm going to show this to you with numbers as well. Let's clear that. All right, so here we have the first ionization energies, and here we're just going across the second period of the periodic table. And you can see, as you go across the periodic table from sodium to magnesium to aluminum, that the ionization energies in general do increase. Now, second ionization energies. Sodium, it goes from 500 thereabouts to about 4,500. All right, that is a huge jump in ionization energies. You don't see a difference like that for any other element. Magnesium just goes from 740 thereabouts to about 1,400. So nothing as big as sodium's second ionization energy. If we go to third ionization energies, you can see that magnesium now has the big jump in ionization energies. It goes from about 1,400 to 7,700. Fourth ionization energies, that is, you're going to see that big jump for aluminum between the third and fourth ionization energy. Aluminum does have those 3 valence electrons, and then that fourth electron is removing a core electron. All right, so that was with numbers. The other ones were more qualitative there. All right, electron affinity is another one of your trends, and this is back on the front of that paper I gave you. If I have an affinity for ice cream, what does that mean? Because I do have an affinity for ice cream. That means I love ice cream, okay? So electron affinity is basically going to be a measure of how bad an